So our goal now is to derive Hill's equation, which is the fundamental equation in our accelerator. Once we've done it, you just do it once, normally in an lecture course. Then once you have the results of that, you then put them in a certain form and you use them time and time again. So once you derive them once, you can be happy. You always go back and understand the approximations made later, but the results you can always use. So what we're going to do is, it's about 10 slides of algebra to do, and we'll get Hill's equation out at the end, then we'll study the properties of them. So we're now going to derive these equations under the influence of only the first two terms in our multipole expansion, the dipole and the quadrupole fields. We will actually come back and study sextupoles in lectures 5 and 6, so we won't stay linear for the whole time that I'm going to talk to you. But the steps we're going to follow are the following. We'll define a coordinate system, a curved coordinate system, and our coordinates really carefully. We'll then work out what position, velocity, and acceleration vectors look like in this coordinate system. So basically that's a bunch of d by dt's of unit vectors in polar coordinates, which you should have done at university. Note we're concerned with transverse motion, and essentially I'll drop longitudinal motion and come back to that later and handle it in a different way. We'll then use the Lorentz force law to figure out the motion, the forces on a particle, and write down an expression for the change in momentum because of this external force. We'll then change the independent variable. Remember, we wrote down the Lorentz force law as Newton's second law is a d by dt equation. That's not so good for accelerators because actually we want, as a magnet, a localized objects in space. We want to use space and not time as the independent variable. So we'll change from time to space. We'll then expand the equations, so we're linear in our transverse coordinates, and then we'll specialize to a case of a pure dipole and a pure quadrupole field. They're the steps we're going to do. The result will be a second order ordinary differential equation for each plane for the motion of the particle in an accelerator, and they're called Hill's equation. So it'll describe the motion of something like this. This is actually the PS at CERN, part of the LHC injector chain. You can see the dipoles, you can see the quadrupoles, and our equations of motion, quite simple, deceptively looking, I think, on paper, describe the motion of the protons going round that accelerator. So I'll just carefully define our coordinate system. I'm going to use a curvilinear coordinate system as develop the equations of motion for a circular or linear machine. Of course, in a linear machine, you wouldn't have the natural focusing terms from the dipoles, but the equations still apply because you still have quadrupoles. So our coordinate system is a right-handed system, x, z, s. I apologise for using z as a vertical coordinate. It still confuses me. I did that because I wanted to match the Villa textbook. I now regret it every day, but it takes me ages to change all the z's to y's. But it's a good lesson in accelerated physics. Books use weird coordinate systems. You'll often see xy, you might see that I'm using xz, where z is vertical and s is longitudinal. You'll see all kinds of weird symbols for the different planes because it's a very international subject. So it's good to keep in your head clearly what's going on and what coordinate means what. You can see I suffer because I made the decision a couple of years ago to use z in these lectures, but I still write y in half some of the equations because that's what I naturally think of in my head. So just be careful is what I'm saying. And get used to this subject where it's a bit, the conventions change a lot from textbook to textbook. So we'll use a curved coordinate system, and this is it. So that's our accelerator. The path, the longitudinal variable is going to be s. Z is our vertical direction, and x is our horizontal motion direction. Rho is the rate of curvature of the reference particle. So the local curvature is rho, and the path length along this curved trajectory longitudinally is going to be s. So the position vector of a particle in this system, r, is given by a two-dimensional vector, ignoring longitudinal coordinates, r, which is x plus rho along the x direction, plus z, the vertical coordinate, along the z hat direction. Notice straight away we've broken the symmetry between horizontal and vertical. We're bending in the horizontal plane, not the vertical plane, so we're going to see focusing terms horizontally, we won't see vertically. That's, remember the little dots moving around circles, that's just that bit of physics. Also notice that the direction, think back to your first year undergraduate studies, the direction of x vector it's going to change as you go around the circle. So vector x dot is non-zero. That's something we tell our first years at university and still confuses them. So I'll tell you about it. So the curved reference trajectory is called the orbit, and the coordinate system moves with the reference particle along the design orbit defined by the dipoles. So our coordinates, x and z, ignoring longitudinal for a second, represent deviations with respect to the ideal design orbit. And we assume these deviations are small. Do you remember the closed orbit in the LHC I showed you right at the start? The deviation was millimeters. That's our x and z coordinates in this case. And for coordinates of design, we also use the position and also the slope. So we won't talk about, as you formally should do, the horizontal conical momenta. We'll talk about dx by ds, and we'll label that x prime. That's what's normally done in the subject. That numerically is the same as the normalized transverse momenta, but it's slightly less well-defined quantity, but I'm following the standard textbooks here. So our coordinates are going to be x prime, z prime, plus some longitudinal ones, which we'll worry about in a few lectures' time. So I'll put this slide in again because I should make it crystal clear what a coordinate system is. So it's an extra same information written differently because it's well important. So that's our picture, particle moving around the slope, x and z are our coordinates, bend radius rho, the design of this curvature rho, the path length along the orbit, so around the circle, we'll label it by s. That's the distance through the accelerator. But we'll start off not with s, but t as the independent variable. And we'll make a switch from time to space. We're going to ignore longitudinal motion. That's why I can be cavalier, and s is my independent variable, not the longitudinal coordinate. I don't have longitudinal motion. We'll come back to this in lectures 5 and 6. So every point in the accelerator, we have a coordinate system, x, z, s, where I've been cavalier with my s. S is really an independent variable, but think of it as the distance around the accelerator. We'll be more rigorous on s later, but essentially we're going to drop s. So a bit of dullness we have to do. You may have seen this before if you've got a physics background, or if you haven't, don't worry, it's all straightforward. You have to just do some kinematics. So our position vector is rx plus z vector. We want the velocity and the acceleration. We have to differentiate. So the v is just r dot, and if we do d by dt of this thing, we get 3 terms, because z dot vector is 0, because it's always pointing up, but x vector dot is non-zero. So we just use the product rule to expand out the apply the operator, and we haven't thrown away this term because x vector changes as you go around the circle. This is just standard circular motion. Then we just note that x vector dot is just theta dot in the s direction, which you can derive from a nice single sexy picture, or look in a textbook on dynamics and circular motion. I'm not going to derive that because that isn't the point. We haven't got time to derive every little result. So we end up with 3 terms, and this is our velocity vector. It's got an x vector component, an s vector component rising from the x vector dot component, and z dot z vector. But we're going to use Newton's second law, so we need the acceleration vector. So we have to differentiate this thing again. So we differentiate it again. Again, we're going to pick up a whole load of terms. We're going to have 2 terms from that, 3 terms from that, because r could be dotted, theta could be double dotted, and s changes as you go around the accelerator, and we only have 1 boring term from the vertical motion. So we end up with 6 terms. Then we just use the fact that s vector dot is equal to minus theta dot x vector, which again is a standard result from circular motion. You should have seen that before in previous courses. If you haven't, you can look at any accelerator physics textbook. It's just there. And if you just collect the results, we end up with our expression for r double dot in our coordinate system as a bunch of 1, 2, 3, 4, 5 terms. I would suggest you don't sit there and do the differentiation. Look at the structure of the calculation and just remember to come back and just do it and just do the substitutions. It's just standard. So that's the boring bit. Now we have to figure out what this is equal to. So we have r double dot geometrically. That's That's just the geometry of the motion in Newton's second law. We have to then find the force. What's the force on the particle in this coordinate system? Well, to find the force, we just use the Lorentz force law, with no electric fields and only transverse magnetic fields. Two assumptions there. One, we're not worrying about accelerating cavities. Two, we're only worrying about transverse motion. And that will become clear why as the course goes on. So we want Newton's second law, we need dP by dt, basically, which is given by E V cross B. So we just need dP by dt, which is just given by d by dt of m gamma r dot or m gamma r double dot. So you have to find this quantity. I know this is the boring bit. We'll get the good physics in a sec. So we need dP by dt. So we've got our coordinate system, we've got our velocities x, z, and v and s, and we have only transverse fields bx and bz. We take the cross product. I guess you can do cross products. You do that. Then we have an expression for dP by dt. Why is that good? Because dP by dt is d by dt of r gamma dot, or equal to m gamma r double dot. I've assumed that gamma dot is 0. So d by dt of attacking this, operating on this, there's going to be a bunch of terms. M dot is clearly 0. The r double dot term I've retained, and I've dropped the gamma dot term. Because, again, that's an exercise. If I only have magnetic fields, gamma dot must be 0. And I'll leave that for you to prove. To get gamma dot equal to non-zero, you need electric fields. So in our simplification, no electric fields, gamma dot is 0, or the energy of the particle is an invariant. So boring bit almost over. So now we have an expression for dP by dt is equal to m gamma r double dot, which equals this lot. So we have an expression now, so we can equate this to this and look at it component by component, dropping the longitudinal bit. This is the hard bit over. So what we've ended up is we've dropped the longitudinal part. We've got an equation for r, a differential equation for r, where r is rho plus x, in terms of derivatives of r, a geometrical term in terms of the field seen by the particle at a given point in S, and also an equation for z, which is the vertical equation. So the details, the notes will be online and printed, so you can go back over and check the details. But we have the Lorentz force law, we have some geometry, we combine them, we get an equation of motion for r, an equation of motion for z, horizontal and vertical, in the presence of just a transverse field b, x, and bz. That's what we've done. Notice the symmetry between the planes is not preserved. In the z equation, there is no term looking like this. That's the equation that will give us our dipole weak focusing. So we have a difference between the two planes. Okay, a bit of tediousness, which I could just write down the results, but I refer you to Lee, but then I explain how to use it because I'll be here all day otherwise. This is essentially these equations, the dots in these equations in the previous slide are referring to d by dt derivatives. So our independent variable is time. That's not so great because as you build an accelerator, you then have to worry what fields a particle sees at a given point in time. So you need to know its motion to get that information. But to get the motion, you have to know the fields. So you're a bit stuck. So, but if we have the equations in terms of independent variable of space, I build a quadrupole and I put it there. So I know the field seen by the particle at a given point in space. I control that. So independent variable being space is much better than time. So on this slide, all we do is we change our d by dt's into d by ds's. That's what we do on this slide. And we do it by thinking, well, hang on, I should know that because the obvious thing to do is ds by dt is the longitudinal velocity v sub s, isn't it? That's the obvious thing to do. But it turns out that's wrong because there's an extra factor because of geometries of the orbits. And I refer you to Lee to understand this. But essentially, we have to scale back from the orbit the particle's actually on to the reference orbit, which is where v sub s is. So that's the origin of it, some geometry. But what it means is, if you look at Lee, ds by dt is not v sub s, ds by dt is v sub s times rho over rho plus x. That's the geometrical factor. So that doesn't matter too much because I'm interested in the structure of the derivation. So all we have to do is change our derivatives. So r dot is dr by dt. So we can just change this into a dx by dt derivative because r is just rho plus x, and the same goes for r double dot. So we just swap the derivatives over. Now don't drift off here. We'll finish the hard bit. On the next slide we'll look at our equations. So that's on the slides for you to look at in your own time. So what are the equations of motion? We're almost there now. We've done our game, apart from one little bit on the next slide. So we've changed the independent variable from t to s from using the Lorentz force law. We've swapped the dt for a ds. We've then got a bit of geometry to play with. We've got an r theta dot term, which is equal to v sub s. And we just manipulate that into v sub s squared over rho plus x. All the equations are there. We stick everything together. We do 10 lines of algebra, 5 lines of algebra, roughly. And we end up with this. This is our differential equation for x, once we've just done this variable change, where we've got a d squared x by ds squared term, so it's a spatial derivative, not a time derivative now, got the geometrical factor. We've got this term coming from the natural focusing accelerator, and we've got this term coming from the field. There's a similar equation for z, which is just this term is dropped, and that is a positive sign, as you see in the previous slide. It's really worth working through this on a piece of paper yourself. See, PowerPoints are rubbish for derivations, I think. You need a blackboard. So either you do it on a blackboard and do it properly, or I give you the overview and you go off to a library and work it through yourself. There's for me, no intermediate out. Every single line of this on PowerPoint is just stupid. It's the wrong medium for it. So that's why I've skipped a few lines. So don't persecute me for that. It's just the limitations of the medium. So we then have this bit and this bit, which we're interested in linear differential equations for x and z, our variables. These are not linear in x and z because there's complicated x dependence. So the next thing we do is we expand our equations out and for x and z and only keep the linear parts of those equations. What that means is this thing we do an expansion of, this thing we do an expansion of, we stick these terms into there, we expand everything out. Anything that's not x to the first power, we scratch out, and we're left with only the linear parts of our equations. If we do that, we end up with this, where this term has become this term has become this term, and we've got this term on the right-hand side, where we've now subtracted from b. See, that should be a z. Oh, stupid. I need to change that. So if you see y, read z. This is my own fault for choosing z as the vertical coordinate. Never again. But notice now, instead of having just bz, we have bz minus this thing. Now this thing is actually just equal to 1 over rho, because when we do the expansion, we pick up a 1 over rho term here, which we then bring over to the right-hand side. So this field here is now the field actually seen minus the guide field. This will make more sense in the next slide. And the equation vertically is then equal to this. And notice these are both linear in x. So there's no x squared terms, there's no x times this derivative, for example. That actually went in the derivation. We only have linear terms in x. We also made an assumption that the momentum is given by m gamma v sub s, i.e. we can ignore the transverse momenta of the equations. So essentially we're dealing with ultra-relativistic particles. And finally note, we've normalised everything by rigidity. Remember the rigidity P over E? That's now appeared there. So everywhere where this field appears, the field appears divided by the beam rigidity. That's the only thing we ever deal with as accelerated physicists. We don't deal with the raw field. So, last bit of effort. In principle, this BZ could be an arbitrary function of x and z. We're going to specialise to a particular case that we discussed before coffee, only if we have a constant bit and a linearly rising bit, the first two terms of our multipolar expansion. So B is now no longer arbitrary, B is actually a constant term in the z direction to give us the motion in the circle. And on top of that, it's got the form of the quadrupole that we established before coffee. So there's no quadratic terms in this field. Essentially, this is the first two terms of the B field Taylor expansion, where the gradient is partial dBz by dx. Now, if we do this, something quite odd happens. And first, after that, that's a bit odd. So remember, so that's our form of the B field. If we stick this in, what happens is that the guide field term BZ0 actually cancels. Do you remember we had BZ minus BZ0? If we stick BZ equal to that and that in, the BZ0 goes away. So when we stick our equation, this field, into the previous slide's equations, we end up with this equation for the motion in the horizontal plane, where G is the quadrupole gradient, normalized to rigidity, and 1 over rho squared is the natural focusing term. So I used to wonder, where the hell has the BZ0 term gone? You don't need that to go in a circle. Well, this equation is now describing motion with respect to the curve reference trajectory. So the constant B term no longer appears explicitly in that equation. It's oscillations around the curve trajectory. So there's no explicit BZ0. So you can try that for yourself and stick it in and see the cancellation. So that's our equation of motion for the horizontal motion, and that's our equation of motion for the vertical motion. It only depends on the gradient G. So in some sense, we've just finished the derivation of these equations. You probably think, well, I think we understand that. If you did, brilliant. If you didn't, that's because I zoomed over a couple of bits of it for two reasons. One, on PowerPoint, you can't really go into the nitty-gritty of it. And the second is, forget about the details. The details are written down on my slides in the textbooks. Look at what we've done and think of the steps we've taken. With coordinate system, we wrote down the equations of motion, we linearized them, we then specialized for the case of a dipole and a quadrupole field only. And we ended up with these equations. Now these are Hill's equations for the motion and accelerator in the horizontal and in the vertical plane. So we'll do it again explicitly, but just think in your head, think to our pendulum equations, where we had some derivative with x plus some constant times x equals 0. So the sign of this guy here will determine if the coordinate x oscillates or diverges. So by playing with the weak dipole focusing, but then mainly with the strength of my quadrupoles, I can have oscillatory motion in the x-plane. But because the x and the y planes are linked, because the B field is curl-free because of Maxwell's equations, the same G also appears in my vertical equation of motion. So you can look at the derivation later, but we just look at the end result as being an equation of motion horizontally linearized an equation of motion vertically that depends on the dipole parameters and depends on the quadrupole gradient. If you're still troubled by BZ0 cancelling, that can be a great a tutorial discussion topic. So the fields like G are periodic functions of S, so they have a periodicity equal to the machine circumference or the length of some repeating period, and we have derived equations for motion transversely. We dropped along the way all S vector terms without really mentioning it. That's because this framework is not really suitable for longitudinal motion. And also notice, imagine G was some number. Ignore for a second this term here, cross it out. Imagine G was 4 plus 4. That means we would have stable oscillatory motion in X and defocusing a diverging motion in Y. So the nature of Maxwell's equations means that we can only with a quadrupole focus in one plane and diverge in the other. I mean, this was confusing. Some authors play with the sign of pieces in the second term of the equation for X. For example, if you open Villa, the textbook Villa, you'll see minus G over B rho plus 1 over rho squared. Because that's to do with the definition of your quadrupole gradient. So be really careful. I've picked a convention for the sign of these terms as being the same, but you don't have to. Different books do different things. So that's our convention for our discussions. So, exercises not for now. So prove that the B field bends the trajectory of a particle but does no work on the particle. This means that energy does not change. So essentially, I'm asking you to prove in just B fields d gamma by dt is equal to 0. That's fun, and that we use that in our derivation. And also, we've used magnet forces for transverse motion. If we've done that, what does that mean about our longitudinal control of the beam? What control do we have in this situation? Okay, hard work over. Now accelerated physics comes back. So after some effort, we've derived Hill's equations. They're linearized, second-order differential equations for our transverse variables x and z in a dipole and a quadrupole field of a particle accelerator. That's what they are. If you want, block out the previous 20 minutes and just look at the final result and look at the physics of it. And that's them here. So we have x, or x-coordinate, which has this focusing term with the quadrupole and the dipole bit, and then have the vertical contribution only the quadrupole bit. So in the equation of x, g, hang on, I'm stuck on the chair. X, g comes from the quadrupoles, but also as 1 over rho squared from natural focusing of the dipoles. So what we're going to do is we're going to solve these equations in a second. But we assume that k and rho are constant in the solution. So we assume that in that derivation, k didn't depend on s. There was no complexity from that. So what we do is we assume these are piecewise constant functions. So the differential equation where g and rho are constant, this applies with them being constant. We then go to the next bit of the accelerator where they're different but still constant. So we have the same equations where they're still constant, but there's no worry about the fact they're changing with position, if you see what I mean. So as we go around the accelerator, rho and k depend on position. And we can compactly write Hill's equations in both planes. If we generically denote x or z with just u for an arbitrary plane, and writing the position-dependent spring constant as k, we can just write this equation. Where this equation here is Hill's equations, Hill in one for both planes, and what k, big K is, depends on what plane you're in, if you're in a quadrupole, if you're in a dipole. So we just go off and solve this equation for arbitrary big K and understand the motion in both planes at the same time. And that's what we're going to do. But that's a dead easy equation. You know what that equation is. It's a pendulum equation. I've already solved it. So as like a master summary of up until this point, we've derived our transverse equations of motion. That's the most painful bit of today out the way. We can now have the fun of looking at these equations and understanding the motion of particles and accelerators. That's Hill's equations. D squared u by ds squared plus k times u is naught, where this k depends on what plane you're in, where if we look at the horizontal plane, we have a quadrupole bit and we have a natural focusing bit, or the vertical plane, that should be a z, not a y, bugger. So I got it right there. Then we have the term in the vertical plane. So our goal now is to solve them, dead easy. But just one word on effective magnet lengths. You'll hear this as you talk to real people doing real accelerator design. We've changed our equations of motion to have s the independent variable, but it's not the case that when you enter a physical magnet, the field suddenly starts. In reality, here we have, for example, a dipole, and here we have the field of the dipole as a function of length. This here denotes the length of the steel, and this is the true field shape seen by the beam along its path. So the length of the magnet is not the same as the magnetic length of the magnet. In our equations, we always use magnetic length, not actual physical length. As beam dynamicists, we don't care where the metal is. Other courses will when you design magnets, but for us, we don't. We just care what the beam sees. So when we discuss length, we often talk about the magnetic length, which normally extends further than the actual physical length of the magnet. That's just be careful. So now we have to solve it. And what we'll do is we'll solve it. We'll then observe it's linear, and we'll then write everything in terms of matrices. And these are the matrices that everyone talks about, basic beam dynamics, everything in terms of matrices. And you can say that kind of makes sense because what matrices are is a representation of linear algebra. And we've linearized our equations of motion. So it kind of makes sense we can use matrices to describe the solution to linear equations of motion. That kind of makes sense. So here are equations, but really hard to get them. X, we have now written G over B rho as K, and the dipole focusing term equals naught, and the same for the vertical plane, where we have Z, and now I've used a prime to denote a spatial derivative. I've just brought that in without telling you. And so we can write big K as equal to K in the vertical plane, or big K is K plus 1 over rho squared in the horizontal plane. So we've got to solve these equations. Forget about quads and dipoles for a second. Just look at it as a differential equation for big K. Just do that. So if you look at that equation, what happens if K is greater than naught? If K is greater than naught, we have X double prime plus K times X equals naught. Forget about accelerators. That's a mathematical problem. We solved that before coffee. And we just have this solution. It's just the same as a mass on a spring. So X of S, so in our sense, our transverse particle coordinate is a function of longitudinal distance of the accelerator, is now given by some constant times cos root ks plus some constant times sine root ks. That's what's happened. So the question is, first of all, does this obey the equation of motion? Well, to do that, we just take the derivatives. There's x prime, and there's x double prime. That's a simple elementary example in differentiation. Substitute it back in, and you find indeed that it obeys the differential equation, provided root k is given by omega, where omega is the thing that appears inside of there. So that trivially obeys differential equation. I haven't got to tell you that. That's obvious. You can see that. So this solution seems to work. Of course, we assume k was greater than naught, so it's a symmetry, sine and cosine. But we'll come back to the other case later. I mean, obviously, it's going to be sinh and cosh. How about the unknown constants? Well, we can fix these in the initial conditions. So this is describing essentially a region accelerator where we have some k, which is a mixture of quadrupole and natural focusing from dipoles. So we go into that bit of the accelerator with some particle coordinates, some x and some angle, some x prime. So if we just let s equal naught be the start of the magnet, the effective length of the magnet, which is a sensible thing to do, the particle arrives with x naught and x naught prime, which is good. Then if we just substitute this into the equation on the previous page, we can fix the constants. And we can fix the constants c1 to the x naught and c2 to the x naught prime over root k. That's trivial. Just do it on a piece of paper, which means we've now solved our equations of motion. So now we understand how x and x prime evolve through a magnet which has big spring constant k, which is positive, if it goes in at some position and some angle. So that means if you have some dipole or quadrupole in the accelerator, particle goes in, we can now calculate how it comes out. That's what we've done. We've got the position and the angle as a function of position through the magnet if it goes in at some position and angle. And it's just equal to this, where that's the cos and that's the sine solutions. For x, to get x prime, we simply differentiate it. We just differentiate the solution. So that's good. So by sleight of hand, by understanding pendulums, we've written down the equation of motion in a quadrupole. We then solved the equation of motion in a quadrupole, so we can calculate the position of a proton on the LHC through a quadrupole simply by using these two expressions. So actually, we've done quite a lot. Now, what does it mean? Now, what happens is that imagine a bit of accelerator where there was no dipole field, it was a pure quadrupole, and it was a horizontally focusing quadrupole. So G, the gradient, was greater than naught. This is our quadrupole. What we'd like is it to focus the motion horizontally. So it comes in off axis with some x, it receives some kind of kick. So what a quadrupole really is doing, a focusing magnet horizontally, is kicking your angle, horizontal angle, back down. So your motion is not going out, it's now coming in. That's what you want it to do. If you just look at these equations of motion, you see that the outgoing angle of the quadrupole gets a negative kick, if that's positive, back down towards the axis. So what the quadrupole does is gives you a focusing term. So this solution means that any particle going out is then focused back in. And also note the final coordinates, the final x and x prime, are linear combinations of the initial coordinate. So the final coordinate, the final x, is a certain amount of the initial x plus a certain amount of the initial x prime. Not initial x squared or initial x prime squared, something like that. It's a linear combination, whereas the coefficients are really just the magnet parameters. So that's what a quadrupole does. It does focusing. So we can write our result using matrices very, very compactly. So if you have some initial particle going into the quadrupole, initial point naught, the final result, the final x and the x prime at position S, is just a vector of x and x prime times by some matrix. And we can do that simply because if we look at these equations, they're just linear in x and x prime. So the new x is a certain amount of the old x plus a certain amount of the old x prime. That's just the expansion of a matrix equation. And the same goes for x prime. So we can write those two equations really compactly as a matrix, where this vector here is the initial particle coordinates, that's the final particle coordinates, and the quadrupole is somehow represented by this quadrupole matrix, its action on the particle. And the matrix itself is written like that, cos, sine, minus sine, and cos. So in some sense, we've really abstracted ourselves away now. We started off with complicated equations of motion, we then solved them, observed the solutions are linear, and now we have a very, very abstract form. We have some particle at naught gets hit by some matrix to give you the particle coordinates at the end of the quadrupole. So our linear equations of motion have really worked in our favour. So that was the case of big K greater than naught. What about big K less than naught? Well, big K less than naught has this equation of motion, where this now has a negative sign. This is like a diverging system, so not like a nice pendulum solution, but a nice diverging sinh and cosh. So just going back to our math on a spring studies, we could just use sinh and cosh and find that the trajectory of the particle is not given by sines and cosines, it's now given by cosh and sinh, where we now have to take a modulus sign inside of there because big K is less than naught, and we want to have a real solution of our square root. So that's good. This corresponds to a defocusing lens. So what happens is rays could be like this, so that's at x and some angle, comes in, hits the lens, actually gets a kick back out to larger transverse position. You can see that by differentiating this, what's done for you there, and you see that the change in angle is proportional to the positive initial coordinate. So if I'm at some large initial coordinate, my kick is the larger angle. So I get pushed out. I don't get focused, I get defocused because of the sign of this term here, which is good. There's a lot of physics in there. I suggest you go back and derive these equations by going through the slides, paying real attention to the signs, because the signs are giving us defocusing and focusing behavior. So I can differentiate this to get x prime of s through a defocusing quadrupole. Again, it's a linear in the initial coordinates, and I can write the matrix for a defocusing quadrupole, not in terms of sines and coses, but in terms of sinches and coshes. So what we're going to do is we're going to solve Hill's equations in a piecewise way. Well complicated. In principle, k and rho depend on s, arbitrary functions. We'll solve it for constant values and then sort of glue these things together. So the motion through a quadrupole is given by a matrix. We'll use that matrix, do a drift by another matrix, and we'll build up the solution through the accelerator. So a quadrupole, because of Maxwell's equations, we looked at this before, focuses in one plane and defocuses in another. So if we have the sine of big K, tells you if it's focusing or defocusing in a given plane. And by convention in the field, we call a horizontally focusing quadrupole a focusing quadrupole, if you see what I mean. And a vertically focusing quadrupole, a horizontally focusing quadrupole is a focusing quadrupole. So if someone says to you, I've got a focusing quadrupole there, it means it's focusing horizontally and defocusing vertically. If someone says, I've got a defocusing quadrupole there, it's defocusing horizontally and focusing vertically. Okay, what about a drift? So we have quadrupole matrices for different signs of quadrupoles. What about a drift? Well, a drift space is what we call in the field a region of a beamline which has no fields in it at all. So no B fields. We could find the evolution for x and x prime by taking the limit of the quadrupole matrices as big K goes to 0, or by simple geometry. Because if you look at this picture, if I'm at some coordinate x and I have some angle, the change in my coordinate x is simply going to be the length of the magnet times the angle added to the original coordinate x. That's just a straight ray through a non-curvy region. Either way, we find in a drift space that the position changes like this and the angle changes like this. So the angle doesn't change, it comes out to be the same in a drift, but the position changes by the product of the length of the drift and the angle, which we can write as a matrix, dead easy. So we have just a matrix with a 1, an L, a 0, and a 1. So that's our matrix for the drift. Just a couple more minutes, just 2 more slides and we can have a break for lunch. Actually, we stopped for the day, don't we? Come to think of it. There's 2 lectures, that's good. We know the matrix quadrupole is this. Often you want to be in the pub, you want to calculate a motion and accelerator. I know you will one day. So often Cauchy's signs are quite hard to evaluate for magnetic parameters. You often don't want to do that. So, but very often the lens quadrupole physical length is short compared to its focal length. Think of your optics courses at university when you did light optics. You have the focal length of the lens. Because the quadrupole is just a lens, it's also got a focal length. So what this means is this focal length actually is given by 1 over k times L. So the strength of the magnet times its length. 1 over this is often bigger than the length. So the length of the magnet is also is small compared to the motion it has on the effect on the beam. So what we very often do in these kind of calculations is you take the limit of a very, very short magnet while keeping the focal length constant. And this makes this transfer, this matrix, dead simple to remember. So if you take this limit, it's like 4 lines of algebra on a piece of paper. This gives what's called a thin lens matrix for a quadrupole, which is really good for quick calculations of accelerator structures. And this is the answer. If you take the limit, try it on a piece of paper, you get this, where this is now the matrix representing the action of a thin lens quadrupole, where it has 1 on the diagonal, 0, and minus 1 over f in the 2, 1 position, where f is defined as big K times L. So that's the focal length of the magnet. How this then works is, imagine that f was bigger than 0 for a second. This means that this 1 over f is some number and it's negative. So the kick applied to x prime is going to be some negative kick. So it's going to bring x prime from some angle back down towards the axis, representing a focusing quadrupole of focal length k times L. So that's quite useful for back of the envelope calculations. You can just in a pub, you can write down a drift matrix, you can write down a thin lens matrix, multiply them together and look at the structure that what happens in a given structure very easily. So now we've got 4 matrices to play with. We've got 4 linear transport matrices that if I have some vector xx prime, these tell me what this element does to that particle. We've got a focusing quadrupole, thick lens variety, we've got a defocusing quadrupole, we've got a drift, and we've got a thin lens quadrupole. So now you have enough information to calculate a simple tracking code, where I can give you a bunch of particle coordinates and you can calculate the trajectory of this particle as it goes through an accelerator beamline made of dipoles and quadrupoles, just by using these matrices. And if you fire up something like mad, in its simplest form, one of these computer codes, what it's fundamentally doing is just multiplying these matrices together. So here's questions for you. How would you turn these into simple tracking code? What would you do? That's like a fun little exercise to do. Here's another question for you. You can then calculate x and x prime as a function of position to the accelerator. When are your results valid? When are they not valid? That's a rhetorical question you should always think about when you use these codes. Anybody can take these matrices and whack them into MATLAB and produce a tracking code and then put it on the internet. But you have to understand yourself when the results are valid. And finally, what's the determinant of all these matrices? This will come back to bite us later. So it's worth calculating it now just to understand what the determinant is. So what have we got left? Yeah, I'll do one more slide. But we have lots of elements. So here's an accelerator. They're dipoles, they're quadrupoles, forming a ring. We know the particle will oscillate transversely. We now know how to calculate the motion of that particle as it goes around the ring, because we know the matrix for a quadrupole, and we know the matrix for a drift. We haven't yet derived the one for a dipole. We'll do that next week. But the question is, how do we calculate the motion of a particle now? Well, each element has its own matrix, and we just multiply the matrices of each element together to give the overall matrix of the whole system. So the matrix to go through this quadrupole is just a matrix. The matrix to go from here to here, it's a single matrix. To get it, we just multiply the matrix of all the intervening elements together, the quads, the drifts, and the dipoles, to get some kind of overall matrix. So we just use matrix multiplication to do the physics of composite systems. So once we have the matrix of, say, one turn of the accelerator, let's call that big M, we can then find a particle with x and x prime at the start. We can then see what it is after one turn and two turns and three turns by simply using that matrix over and over again. Now, to find the motion, we actually have to know the fields and the positions very well. So your job as an accelerator designer, where are your magnets? How strong are they? When you know how strong they are, where they are, you can compute the matrices of them. You can then calculate what the motion is. Is it doing what you want? No, it's not. Go back and change the fields and keep going until it somehow does. Right, that was the hard bit over. Now things get more abstract next week. So next week we'll zoom out, we'll forget about particles, and we'll start to worry about macroscopic variables, and we'll look at what's called a Curran-Snyder formalism, which is the way most people in this building will design accelerators. So that's what we'll do next week. Okay, I'll see you next week.